Yeah. Hello, hello, hello. So, so let us start today's proceedings, and by the time if people joins, that would be great. And we'll start uh, today's discussion on the power electronics applications in power systems. And it is week 11, and this week we have seen Sir has taught various things on StatCom and Triple SC. Okay, so I'll just have a brief overview of these, and then we can start the numericals or question answers from the previous year assignments. And so let's proceed. So basically, uh, we have seen things on PCSC, so thyristor control. Yes. So under the broad category of compensators, we have seen that the power electronic compensators, like this compensation techniques, right? So excuse me. So it can be categorized into shunt and series. And one category of shunt compensators, sir has already covered those part. That is the thyristor control segment. So thyristor control reactor as well as capacitor. And its derivatives. So not only this, so it has additional varieties to cover. So here the major segment in this part is the statcom. So it is static synchronous compensator, and the main difference is that here we have a variable susceptance, that is uh, variable susceptance to deal with the so xc or means xc or xr or x capacitor or reactor. So this we have already, we know that we can have a variable, but in the statcom this is converter based approaches. Converter based. Okay. So already we have seen that this statcom has two broad segments: is application in transmission and application in distribution systems. Application in distribution systems. Okay. So hello. So I think I'm audible. So since there was no one, so I was going through the overview. So if you are have any doubts, you may ask, or we can switch to the question answers of the previous assignment. So as you wish. So I think it was mostly a theoretical segment and few numerical type questions I have with me based on the previous year assignments and all. So this was just the overview of what sir has already taught, and so we can start with the questions if you are willing to do. Okay, so I hope it was clear. Okay, then we can start with the questions later if we get. The main aim of these converter based is that by changing the angles, firing angles, we can vary the reactive power. So ultimately we will have to maintain the voltage. So to maintain the voltage, so reactive power control needs to be done, and accordingly we can see to it. So, starting on with the questions. We have just started the question, so you may participate. And in the meantime, if you have any doubts, you may ask. So this is the question: which of the following is not an application of STATCOM? So reactive power compensation in both capacitive as well as inductive mode of operation, voltage control in power systems, backup power during high load demand and grid outages, or enhancement of power system transient stability. You may please write the answer in the chat box, or you may please say by unmuting. Any answer? Please feel free to answer, and we'll just match with the.
I
Yes,
think C will be the answer, sir.
C is the answer. Yes, yes. Because voltage control, it provides transient stability. It also provides reactive power compensation. So C is the answer. Yes. So moving on to the next question. Uh, the inductive. So this is the question. The inductive or capacitive mode of STATCOM is based on these four options: varying capacitive susceptance, varying inductive susceptance, controlling its active power output, controlling its output voltage.
D will be the answer, sir.
C is the answer. So compared to SVC for reactive power compensation, STATCOM offers lower cost and easier installation, higher efficiency and faster response time, simpler control mechanism, or more limited operational range.
D will be the answer, sir.
Yes. Each of following. So this is the question. Distribution system facts or compensation device. Directly from that table.
B answer, sir.
So this is the question. I hope four options are visible. The interface
D
is
will
state.
be the answer, sir. D.
B for Bombay.
No, sir. B. D for doll.
Yes, yes, yes. Four options will take this much. So this is the question. So I hope it's visible. Related to
C
transient.
will be the answer, sir.
Which one?
C.
Mm, for same ratings of SBC and Statcom, SBC provides greater stability margin. But just recall the. I hope if you have the um, lecture notes PDF with you, so I would recommend just to give a glimpse of what the two stability margins. You will see that Statcom stability margin is higher. So if you have it in your mobile or anything, you may just give a look because
Okay.
in both the cases the stability margin. So what sir has shown is that this is the graph, right? So with the variation in the angle, with the variation in with the angle, so this will rise, right? So but in case of SBC, it will rise up to a certain point and it will decrease. So if this rises up to this point, means let's say both are following the same line, Then also this, let's say this is for okay, just let me redraw it, because one first of the first case is that with the variation in the angle of statcom means converter angle, we can achieve higher stability margin. But let's not go in that case first. So for the first case we may see the this is the, let's say both are following the same trajectory. Just we'll just erase it once, because now I can start again. So 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 this is for statcom, and let's say this is the initial operating angle. Okay, so with the disturbance also, this may go up to this point, and at a certain point of time we can see that if these two areas match, then it will, the system will be in stable condition. But the thing is that let's draw the same characteristics of SBC. Okay, so it will go up to this point, and at a point, certain point, it will follow. Whereas if nothing would have been present, the graph would have followed this line. So in these three of these cases, so this is a, let's say this is a semicircle type. Okay, so this green is showing without any compensation, and this green is sorry, blue is with SVC, and this red is with, this is the red. So this red is for statcom. So in all these cases, what we can observe is that in this, for this green patch or green line, we can say we have, let's say this is the stability margin. So beyond this, system will uh, not be operating in a stable condition. And let's say for this value, for using SVC, this much enhancement we have obtained. Okay, this much stability margin enhancement we have, definitely stability margin improvement we have obtained. But using this, I would say statcom, a further increment in stability margin is obtained. So in any of these cases, statcom will have higher stability margin than SBC. Okay, so this is the uh, delta and P curve. So in all these cases, so this question, stability margin increases will be the correct answer. Means in all these cases, statcom will have higher stability margin, whatever be the case. And if the angle is further means the operating angle variation, with the operating angle variation, this line can further reach higher. So in every cases, the stability margin will be improved more than SBC. Okay, so that is the option. I hope it's clear.
Yes, sir. Yes, sir.
So stability margin increases will be the correct answer. So question number 6, 7. Yes. So this is the question.
I think C will be the answer, sir.
See, so I would just like to state that in C it's given capacity mode of operation in the magnitude if output less than. So uh, output voltage magnitude if it is less than the system voltage, that means there would be. I'll just draw the. So sir has already drawn in his lecture. So if you could just recall that if it is the statcom connected here, let's say, and this is the grid. So we have this is the statcom voltage. Let's say this is the grid voltage. This is the statcom voltage at some angle alpha, and this is the grid voltage. And here we have, let's say, some reactance or impedance. Let's say. So if it is V angle 0 and if some angle alpha, if the statcom is operating at some angle alpha, so we can deliver anything to the grid. Okay, only if the magnitude of its output voltage is greater. I would like to state that capacitive mode of operation. That means if we just see the equation of, let's say this was the capacitive or statcom voltage. It was, I hope this was VC. So let's say VC uh, and this is x. Let's say x line. So we see xl and cos alpha minus v square by xl. So we can also write in the form that v by xl. So this is the reactive power flow. So Vc cos alpha minus V. Okay. So this V is the grid voltage and this Vc is the statcom voltage. So what we can observe is that if we don't have means, let's say this is the magnitude of its output voltage as you have pointed. If this voltage output voltage is less, so in any of these cases output voltage if it is less, then oh, another point of operation, that P is, what is P? So P is VVC sine delta, sine alpha by XL. So in each of these cases, our aim is that alpha should be zero. So if alpha is zero, then real power flow is equivalent to zero. So real power flow will be blocked. So here again, if alpha is zero, then we can write this as V by XL, and this is Vc. So Vc minus V. So considering alpha equals to 0, so cos alpha equals to 1. So now we can observe that what will be Q if Vc, as we have pointed that output voltage, that means this is the output voltage, system voltage is V and this output voltage is Vc. Let's say. So is if Vc is less, if Vc is less and V is more, so in that case uh, system voltage, huh? So in that case there would be, this case is for inductive, so this is not capacitive mode of operation. So in order to feed capacitive power to the grid, Vc should be more than V, then only reactive power flow will flow from statcom to the grid, right? So in this case Vc should be more, so capacitive power will be fed to the grid and voltage profile will be improvements. We, to feed capacitive power to the grid, the Vc value should be high and V value will be should be less. So Vc is high in which case? So this is the output voltage is greater. So this is the right answer. I hope I have clarified upon it.
Yes, sir. Yes, sir.
So option D is correct. Okay. In this case, A is, yes, yes, I have marked. So that is so moving on to question number 8, I guess. This is 7, yes, 8. Yes. Ah, so this is the question. So I hope it's clear. SCATCOM can be used for power system oscillation damping by this following. So we can modulate frequency, we can modulate magnitude.
B will be the answer.
Yes, B will be the answer. Yes. So now we have numericals, I guess, for this assignment. Yes. Okay, yes. Continue. React only. This is numerical type question. Consider a three-phase lossless balanced transmission line. Injects. So bit lengthy question. So this is the question. Okay, so this is the question. So consider a three-phase lossless balanced transmission line equipped with STATCOM at 200 kV bus. The STATCOM is connected through a step down transformer. So this is transformer. Transformer I have written in short. Of leakage reactance. Okay, just I should omit this transformer. Leakage reactance X sigma per unit. The STATCOM injects 400 kVAR reactive power into the system corresponding to the STATCOM output voltage VC equals to 1.05 per unit. Referred to the grid side of the step down transformer. Consider the bus voltage remains constant at 1 per unit. Determine the STATCOM output voltage for which the reactive power injection is increased by 100 kVAR. So these are the options. So please give a try and we'll just then discuss. The question is bit lengthy, but the solution is not that much.
233.75 kb.
233.75, right? So I'll just check. Yes, 233.75 is the answer. Great. So, so this is the correct answer. So, so reactive power injection. Let's say it is Q. Right. So given this value, so we already know that Q is directly proportional to BC minus V. And so Q1 is given somewhere 400. Yes. So 400 is Q1 and the voltage which is VC1, this is the output voltage. Now consider the bus voltage to be maintained at 1 per unit. So V is this one. So V is this one. So we can directly write now. And this increases by 100 kVAR. So now Q2 is 500. So 400 plus 100. So this is the increment. So we can just solve one equation and get the final value. So in all these cases, V will have to be maintained at 1 per unit. So Q1 is given. So Q1 is 400 by 500 is equal to 1.05 minus 1 by VC2 minus 1. So I hope if we solve this, uh, VC2 will get us 233. So 220 is the voltage. So if we get in per unit, then also if we convert, I think this will be 233.75, since this is the answer correct and you have rightly pointed out. So this is the correct answer. Okay. So, I think, so so moving on to the next question. Mm, mine. So this is the question.
C will be the answer, sir.
Yes, C is the answer. Yes, C is the answer. So just so so considering the equation, so we know V angle 0 from the grid side. If we look, the KVL current is given I. Current is given I. Yes. So current is J and X sigma is the uh, X sigma is the reactance given, right? So and VC angle, this one is alpha, some angle alpha. So now here in this case, already this has been mentioned that this is the generic equation. So in this case, this is the determine the per unit current injected by the reactive power. Yes. So if alpha equals to 0, so generally we'll keep alpha equals to 0. So this equation is V equal to J I X sigma plus VC angle 0. So we can state this as J I is sorry, X sigma is zero point 0.1, J zero point 0.1 into I is equal to V angle 0. So V is 1. V is 1 and uh, so 500 reactive power. So for 500 reactive power, this value will for the per unit value. So if we just see the VC2 in per unit for 500 kVAR, so it will be 0.0625 per unit, which is equivalent to this point multiplied by 200. So you can so VC minus V. So sorry, 1 minus VC is 1.0625. 1.0625. Okay, so I can be obtained as so 0.0625 minus by J 0.1. So just multiplied with J and this J, if we is it somewhere given the determine the per unit current injected. So just per unit current injection required. So it will be 0.0 oh, point 1. So 625. So 0.625 will be the magnitude if we consider. So only magnitude is required. So 0.625. So this is the. So I hope this is clear. So we can proceed to the other set of questions. Question 11 is the This is now the set of questions will be a bit of theoretical again. So point me out if some questions get theoretical questions gets repeated. Okay, so that we can immediately drop that because questions might get repeated because it is of another assignment only. Mm, oh, sorry, this is uncontrolled. Okay. Let me just rewrite it. So this is the question.
B answer, sir.
This one, which one?
B. B.
B.
B for both. No,
But
sir. No. C. C is correct answer.
these two first two are from that means category of TC thyristor controlled operations. So TCSC, TC, TCR, so TS thyristor switched capacitor. So this one is converter based compensators. Mm, So this is the question.
C will be the answer.
Phase angle should be maintained at zero in order to have the correct operation because real power should be zero for delivering reactive power compensation. Ideal case, definitely. Sorry. This is question 13.
Capacitive.
Sorry. Phase. Um, yep, this is also easy question.
Leading, sir.
Ah, yes.
A answer.
A is.
D will be the answer, sir.
Independent.
C.
C is.
A.
K is small. The terminal voltage is affected as follows. So
Mm.
with variation of K, unit vary widely.
I think D will be the answer, sir.
Yes, 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 yes.
Steady state operation.
Means obviously, I think you missed it with respect to great voltage only.
A will be the answer.
No, statcom voltage phase angle we are discussing. So phase angle should be phase, I guess, because phase angle otherwise reactive power compensation in addition to active power compensation will be taking place. Means active power flow, not compensation, I would say. So both the voltages should be means the alpha value will be must be zero is for ideal operation. So in phase is the correct answer. Is it okay?
Okay, okay, sir. D will be the answer. C.
Uh, if D delta, no, C is not the answer. So it will be increased V because this rate of change of rotor angle in that case or angle means not always the in this case the change of angle. So in that case, the last question it was comparable to voltage support during this can be considered as a fault condition also. So we should increase that the statcom should increase V.
Okay, sir.
So in the this is 23 yes. This is a simple numerical given for StatCom VC is
D will be the answer.
Yes. 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 So so it is given in. Sorry. I hope I have done a mistake. This will be 0.05. Okay. Sorry. Huh. So we know that Q is equal to V VC minus V by. So V is 1.1 minus 1 by point, and this is capacitor positive. So it is delivering power, reactive power to the grid. Okay. So so am I audible? Because might be an internet issue from my end.
Yes, sir, audible.
Because I have written the options, but it was not visible. Means I can't see the options. So,
Yes, sir, audible. Not found correct options, sir.
It's correct. Okay, just let me check. Mm, so basically, it is given reactive current we'll have to calculate. So what will be the reactive current? Reactive current Q. So 100 MVAR. Oh, sorry. I have this will be 100. Sorry. Extremely sorry. This is 100. Okay, just let's solve it. So 100 MVAR is 10 to the power 6 and root 3, and line voltage is given, so 400 into 10 to the power 3. So if we solve it, so it will be approximately 144. If you just check. Okay, so we have one last question, and so it's a simple. So in a steady state,
A option is correct.
A.
Yes, sir.
Mm, So Q is VC minus VC minus by X sigma. So V is given. Oh, hi. So this 400 by root 3, and VC is, so if you solve this, you are getting as 44.4, right?
Yes, sir. Yes, sir.
Uh, yes, this is the answer. So no, no, actually what they have given as answer is option B. So I am also confused because if we consider this 400 as the line voltage, then only it will be coming as 133. So I hope they have considered that as a line voltage, and the reactive power per phase, since it is operated in delta only. So voltage can be kept at 400 only. So yes, so I think option B is right what they have mentioned. I was also confused, so I wanted to check once. Because, so, so option B is correct, not A. Okay. So if you just check the calculation, it will be coming as 133 point something. Just go through once, and I hope this
Yes,
will
sir. 132 kVAR. But when we convert per phase, then this value will be 44.4.
if it is this is might be a, yes, if we divide by 3, right,
Yes, sir. Yes.
per phase, they have given this as, let's do one thing. It may be a mistake, or I don't know these questions whether these were corrected or anything. So well, let's consider the total reactive power. Just omit this so that the question remains correct. uh, Find the reactive power, total reactive power. If we mention, then it will be correct. Let's keep the question correct, and the
Yes, sir.
option.
Yes.
Now the question, I hope this is correct, right?
Yes, sir. Yes.
Okay, that's it from my side. So thanks for joining. If you have any doubts, you may ask. Otherwise, uh, what I will do is that on Friday I have 1 hour session. Means next Tuesday would be the last 12th week. So complete on Friday, I think from 6 only. 1 hour session I will take, so that will be a complete overview of the entire 11-week session, and we'll solve
Yes, sir.
various questions related to these 11 weeks that we have covered. It will be a summary type session of these 11 weeks, and then extra additional. Additionally, this next Tuesday would be the last from my end, as the 12 weeks course is also over, and this Friday we have additional 1 hour. Okay, so
Okay, sir.
solve questions for will be the questions will be relevant to, I'll prepare for the entire 11 weeks, we'll take 2 3 questions from each week and try to solve. Okay. So
Okay,
please.
sir.
Okay. Thank you.
Thank
Thank
you.
you for good night.
Good night.